In this video, we're going to be solving a second example problem using Newton's second law for rotation. So I'm going to do a quick overview of Newton's second law for rotation, and then we will dive into the example. We have an object that can rotate, and in this case, we're going to say that the object is fixed to rotate about a particular center of rotation. We're going to say that one or maybe many torques are exerted on the object with respect to the center of rotation. In this expression here, sum of torques represents the net torque acting on the object. We're going to say that the object has moment of inertia I. That represents the resistance of the object to change in its rotational motion. And as we've seen previously, when we have a net torque acting on an object that can rotate, the result is an angular acceleration of the object. Newton's second law of rotation says that the net torque is equal to the moment of inertia multiplied by the angular acceleration. Here's the example problem we're going to do. We have two children playing on a merry-go-round. This child over here is sitting on the merry-go-round with their feet contacting the pavement below. This child over here is going to push on the merry-go-round. The merry-go-round is going to start from rest, and then as this child continues to push on the merry-go-round will have an angular acceleration up until the angular velocity of the merry-go-round reaches 1 revolution per every 3 seconds. It takes 20 seconds for the pushing child here to bring the merry-go-round from not rotating to this final angular velocity. As this child here is pushing, this child over here continues to drag his feet on the ground so that there is a 30 Newton frictional force acting on the child's feet. We want to find the angular acceleration of the merry-go-round during that 20-second period where the child here is pushing, and then we want to find the force that the pushing child was exerting on the merry-go-round. Let's start by finding the angular acceleration. If we assume that the angular acceleration is constant, then we can write that the angular acceleration is equal to the change in angular velocity divided by the time interval. Let's write that change in angular velocity is final angular velocity minus initial angular velocity. The merry-go-round started from rest, so the initial angular velocity was 0. The final angular velocity was 1 revolution per 3 seconds. And the change in angular velocity from 0 up to 1 revolution per 3 seconds was 20 seconds. Now, if we would simply plug this into our calculators, we would get angular acceleration in units of revolutions per second squared. However, as I mentioned in an earlier video, when we use Newton's second law for rotation, the angular acceleration has to be in units of radians per second squared. And since we're planning to use Newton's second law for rotation in the next part of the problem, we want to get this into units of radians per second squared. So let's put in a conversion factor. A revolution is equal to 2 pi radians. The revolutions cancels revolutions, and we get angular acceleration for this process is 0.1047 radians per second squared. For part B of the problem, we're going to be applying Newton's second law for rotation. In order to do that, it will be helpful to take the perspective of somebody who is looking at the situation from way up here somewhere looking down. So I'm just going to put an eye into the picture, and we can imagine that that eye is looking straight down along an axis that goes through the center of the merry-go-round. So what would this eye here see? Well, the eye up here would see the merry-go-round as a circle. Also, according to the perspective of this eye, that pushing child would be up here somewhere. And I'm going to just represent that pushing child as a hand that comes in to push on the merry-go-round. And here I'll give that hand something to push onto. And then, according to this eye, the sitting child would be over here on the right. So here we have the feet of the sitting child dragging on the ground. Before proceeding, let's put in the forces that the pushing child and the sitting child are exerting on the merry-go-round. Now from the picture, we can see the pushing child pushing to the left. So let's call that P. Let's say that the magnitude of that pushing force is just the letter P without the arrow on top. Now let's come to the sitting child over here who is dragging his feet on the pavement. We have a frictional force between the feet and the pavement. Now, what would be the direction of that frictional force? Well, as that pushing child pushes, can you see that the sitting child here is going to be rotating like so, counterclockwise? The frictional force between the feet and the pavement is going to oppose it by pointing in this direction. So here we have a frictional force, and this would be a kinetic frictional force. I'll just put in Fk without the arrow as the magnitude. And we are given the magnitude of this. The magnitude of that frictional force is 30 newtons. I'll put that over here. Before we go to Newton's second law of rotation, there are a couple of things we need to do to set up the calculation. First, we need to define the center of rotation. So let's just take the center of the merry-go-round to be the center of rotation. Let's also define a positive direction for rotation. Since the merry-go-round is going to be rotating counterclockwise, let's just take counterclockwise to be our positive direction for rotation. Now that we've done the setup, let's write down Newton's second law for rotation and see where that takes us. So Newton's second law for rotation says sum of torques equals moment of inertia times angular acceleration. There are two torques acting on the merry-go-round here. We have the torque from the pushing child and the torque from friction. So I'm going to replace sum of torques with torque from the push plus torque from friction equals moment of inertia times angular acceleration. There are three things that we need to work out here. We need to work out the torque from the push. We need to work out the torque from friction. And we need to work out the moment of inertia. We're going to calculate each of the torques using the moment arm formula, which says that the torque can be expressed as plus or minus the moment arm times the magnitude of the force. So we're going to apply this to both of the torques. Let's work on the torque from the push first. Now, first of all, that push, is that delivering a clockwise torque or a counterclockwise torque? So let's say that this is the merry-go-round, and the push is going to come and act here. You can see that the effect of that push all by itself will be to make the merry-go-round rotate counterclockwise. So that would be a positive torque. Now we need to find the moment arm. Remember that, generally speaking, we find the moment arm by drawing an infinite line through the force vector and then dropping a perpendicular from the center of rotation to the line of force. So here's my infinite line through that push force. And now I go to the center of rotation and drop a perpendicular to the line of the force. So this segment is the moment arm, but you can see that that moment arm is also just the radius of the merry-go-round. So coming down to here, I now have that torque from that push is equal to plus, and then the moment arm is the radius, and then the magnitude of the force is just P. That's what we're trying to find. Now we can find the torque from friction. First is the torque from friction clockwise or counterclockwise. So let's suppose that this is the merry-go-round, and that torque from friction is acting over here, pointing like so. And you can see that that torque from friction all by itself would tend to make the merry-go-round rotate clockwise. So we're going to put that in as a negative torque. Now, what's the moment arm for the frictional force? Well, as before, we will draw an infinite line through the force vector. The moment arm is then the perpendicular distance from the center of rotation to the line of force. So this would be our moment arm for the frictional force. But again, that moment arm is just equal to the radius of the merry-go-round. So coming down to here, we now have that the torque from friction is minus, moment arm again, radius of the merry-go-round, and in this case, let's just put in that the magnitude of the force is Fk, which we already said was 30 newtons. Now for the moment of inertia. We have two contributions to the moment of inertia. One contribution to the moment of inertia comes from the merry-go-round itself, and the other comes from this child that's sitting on the merry-go-round. The pushing child over here is not sitting on the merry-go-round. They are standing on the ground and from the ground pushing on the merry-go-round. So the pushing child does not contribute to the moment of inertia. So I'm going to write over here that the moment of inertia is the moment of inertia of the merry-go-round plus the moment of inertia of the sitting child. First, how do we find the moment of inertia of the merry-go-round? Let's assume that the merry-go-round has approximately the shape of a solid cylinder. So what we can do is go to our table and look up the moment of inertia for a solid cylinder rotating about its symmetry axis. Right. So your textbook or any introductory physics textbook will have a table essentially like this. So in this particular book, I can come right to here, and I have that the moment of inertia for a solid cylinder rotating about its symmetry axis is 1/2 the mass times the square of the radius. So coming to here, moment of inertia of the merry-go-round would be 1/2 mass of the merry-go-round, then times the square of the radius. Now, what about the moment of inertia of a sitting child? We're going to assume that the child is much smaller than the merry-go-round. And if the child is much smaller than the merry-go-round, we can use the formula for the moment of inertia of a point mass. The moment of inertia of a point mass is the mass, in this case, the mass of the child, times the square of the distance from the center of rotation. And since the child is at the edge of the merry-go-round, the distance from the center of rotation is r. So then I square that to get the contribution of the child to the moment of inertia. Okay, so let's see where we are here. So this is Newton's second law for rotation applied to this problem. Let's call that equation 1. And then we worked out the torque from the pushing child and the friction on the other child's feet. Let's call that equations 2 and 3. And then we have the moment of inertia over here. Let's call that equation 4. And actually, before I proceed, let me rewrite the moment of inertia by factoring out the r squared. That'll make things a little cleaner. We can call this equation 5, I guess. Okay, so now we're going to take 2, 3, and 5 and put them into 1. Okay, let's see what we get. So torque from the push, RP, torque from friction, minus RFK, and then I, 1/2 m merry-go-round, plus mass child r squared alpha. At this point, everything in this equation is known except for P, the force exerted by the pushing child. So let's just isolate this and then make our substitutions, and then we'll be done. Let's start by dividing through by r. From there, I can just take that Fk to the other side. So I then have P equals 1/2 mass merry-go-round plus MC, all of that times R alpha plus Fk. Now let's do the substitutions. The mass of the merry-go-round is 200 kilograms, so half of that is 100 kilograms, and then plus the mass of the child would be 130 kilograms. The radius of the merry-go-round is 1.5 meters. Alpha is 0.1047 radians per second squared. And then we're going to add the frictional force, 30 newtons. Before we stick all of this into our calculators, let's do a quick unit check. We're looking for a force here. Force should have units of newtons, so this term has units of newtons. Now, what about the first term here? The first term has units of kilograms times meters per second squared. We also have radians here, but as I discussed in one of the earlier videos, angles measured in radians are actually unitless, and that radian is just kind of following the calculation along to remind us that we are measuring angle in a particular way. It's not a real unit, so we can ignore that. What's left over then is kilograms meters per second squared, which is newtons. So in fact, both of these terms have units of newtons. Putting all of this into my calculator, I get that the push force is 50.4 newtons. And now we have solved a second example problem using Newton's second law for rotation.